Hello everyone, today in this video we'll be discussing the third module of OS which is related to the deadlocks and process synchronization. Make sure you watch this video till the end, easily you can score more than 80% marks, and hit the like button, subscribe to my channel for more videos like this. It helps me make more videos if you like and subscribe. And without wasting any more time, let's get started. So these are the topics present. The first half is related to the process synchronization. We'll be discussing some problems and the solutions and some concepts here. Then we have the deadlocks, and here we have an important algorithm which is the Banker's algorithm. So stay tuned and watch this video till the end. One by one we will cover all the important topics. So let's get started. The first one is the process synchronization. Okay, what is a process? Process is a way of doing thing. Okay, if you want to do something that has a process, okay, so that is what is called the process. And synchronization means you will be having a sync between the different processes so that some mistakes don't happen. Okay, so that's why we need synchronization. So the first concept is producer consumer problem. Okay, let's suppose there is a producer A who produces goods. Okay, like he produces mobile phones, and there is a producer B who packs the mobile phones. Okay, so if producer A produces 100 mobile phones in 1 minute and producer B takes and packs 100 mobile phones in 1 minute, so there is a sync between them, and the number of mobile phones produced is equal to the number of mobile phones packed. So there will be no wastage of mobile phones, or B does not have to wait for some time for A to produce, and A will produce the exact amount. What if in case A produces 200 phones, but B is able to pack only 100 phones? In that case 100 phones will be wasted, right? That is one problem. And second is, if A is able to produce 200 phones but B's capacity is 500 phones to pack, the 300 phones capacity is wasted, because A is not able to produce here, B is not able to pack 300 phones. So this way there is loss of efficiency, or there is loss of mobile phones. That is what is the producer consumer problem. Either producer is producing more or less than required as of consumer's end. Okay, if producer produces more than consumer can consume, there is some data missed, because producers producer more and the consumer cannot consume all that which is produced, so some will be wasted. If producer produces less than the consumer, then there is a loss of efficiency. Okay, there must be a sync between them. Okay, that is the producer consumer problem. We'll be discussing in detail how does this get solved by using a buffer, which we'll discuss in the upcoming topic. Another concept is the race condition. It happens when multiple process manipulate the same data, and outcome depends on the order of execution. Okay, multiple processes are there. Many processes try to access a similar data and manipulate it, means change the data. When that happens, the order of execution, which first, second, third process made the changes, based on that, the last process to make the change will be there as the final change, right? That is what is called the race condition. Okay, next we have the critical section problem. Okay, what do you mean by a critical section? Critical section is defined as a place where all the common variables, updating a table, writing a file is present. Okay, so all the critical section is a place where all the data necessary for the process execution is present. That is called as critical section, also known as CS. Okay, so no two processes should be allowed to make changes to the critical section. What will happen if two processes are allowed? What will happen is, it will override the changes of each other, right? If two processes are allowed, they will write something, the second process will write something, it will be overwritten again. So in that case there will be no consistency in the data. Okay, that is the critical section problem. How do we ensure that two processes should not be allowed to make changes to the critical section? This can be achieved by three conditions: mutual exclusion, progress, and bounded waiting. Okay, what is mutual exclusion? It is such that if one process is accessing the critical section, this is critical section, P1 is accessing it. If P2 wants to access, it will not be given the access, it will have to wait. That will be gone in progress. Okay, after P1 is done, next P2 will be able to execute. That is called as progress. Okay, means the sequence in which the processes will be waiting, that is called as progress. And third is bounded waiting. Bounded waiting means a process can request n number of times only, not more than n number of times. And what is the minimum number of times the process must execute the resource, like that. Okay, means the limits are defined here, how much times the process can request for the resource. And progress is the order in which the processes will be getting the resources. Mutual exclusion ensures that at one time only one process can access the resource. Okay, this is how you ensure the uh, critical section problem is solved. Okay, and there is another solution, Peterson solution for the same critical section problem. So Peterson provides a solution to the critical section problem. It requires two processes share the following data. Okay, if there is a process P1 and P2, both should have this data: int, turn, and boolean flag. Turn denotes that which process will be able to execute the resource, indicates which I is ready to enter the critical section. If turn's value is equal to 3, then P3 will be executing like that. Okay, and boolean flag will indicate is I ready to be entering the CS or not. Okay, turn will indicate which is the next process to execute, and flag will indicate whether that process is ready or not. Okay, so this solution can follow the satisfy the following conditions. Mutual exclusion is given here because the turn is specified, no multiple resources can execute, and progress is also there after one resource, which resource is going to execute, and bounded waiting is also present, one resource can execute how many times. Okay, next we have synchronization hardware. What do you mean by synchronization hardware? It requires a lock. Okay, we have to have a synchronization. For that we need require a lock. Okay, that is what is called synchronization hardware, which utilizes a lock. What does lock do? It prevents other process from accessing the critical section. Okay, if lock is there on a critical section, that means other resources cannot access this. Okay, that is a lock. And lock can be implemented using two functions: test and set and swap. Let's understand what these functions are. Test and set does exactly what it says. Test and set, it will test the critical section if it is able to access or not. If it is able to access, it will set some process to access it. Okay, that's what the test and set does. Swap will swap the content of two words. There will be two data present. If you want to swap the data of it, you will be using swap. Okay, these solutions satisfy the three conditions. Mutual exclusion is satisfied here. Pi can enter the critical section only if one waiting of I is equal to false or key is equal to false. So whenever you want to enter a process Pi, if it wants to enter, either waiting I should be false, means it is not waiting for any other resource, and key should be false. Key means the lock is open. If key is equal to true, means it is locked. If key is equal to false, means lock is open. Whenever lock is open, they can go inside and execute. And once a process starts executing, the key will become true and waiting will also become true. For the other process, they have to wait, right? And next is process. After one process exits, the next process would be kept ready to enter the critical section, thus ensuring the progress. It will not be stopped at any point. The bounded waiting requires that all the process will be visited and ensured that all processes enter the critical section within n-1 turns. So bounded waiting will ensure that whichever process is requested, one by one each of these will be executed. That execution's responsibility is given to bounded waiting. So these three conditions are satisfied in the Peterson solution. Okay. Moving on, we have Semaphore. What is Semaphore? It is a synchronization tool that is used to solve various synchronization problems. Okay, there are many problems in the synchronization, so we use Semaphore, which is a synchronization tool to solve those problems. Now, what are those problems? Before discussing about the problem, let's have a look what is Semaphore having functions. Semaphore has two functions: wait and signal. Whenever a process wants some resource, it requests for some resource, it will call the wait function for that process to wait until the resource is free. And signal means once the process has used the resource and it is exiting from the resource, it will use signal to indicate the other process, giving a signal to them that the resource is empty, you can use it. Okay, so this is the C implementation for wait and signal. Now there are two types of semaphore: binary semaphore and counting semaphore. What do you mean by binary semaphore? It has only values 0 and 1. 0 means locked, 1 means not locked. Okay, it is also called as mutex lock. Mutex means mutual exclusion. Okay, it implements the mutual exclusion because of 0 and 1, at one time only one process can be executing. That is called as binary semaphore. Counting semaphore, it has a range of values. It is used in multi-processing systems, because if there are more than one processors, at that time only 0 and 1 cannot be used. There has to be many more range of values which can be used to indicate if it is used by some resource or not. Okay, so the main disadvantage is a busy waiting. A process has to wait in a loop until the semaphore is empty. So suppose that P1 has requested a resource R, and it is waiting until this resource gets over. Okay, because of semaphore the value is 0 or 1 based on the lock, and once until this lock is over, the process has to wait in a loop. That is called as busy waiting. This is one disadvantage of it. So to overcome this disadvantage, we will be using a shadow process. What will happen is one process will go and request for a resource. Okay, there is a resource here, and one process will go and request for it, and until and unless this process gets this resource, there will be a shadow of it. Means a copy of a resource will be there waiting for the resource, and the original process will go and execute some other tasks. Okay, in this way, whenever the resource is allocated, at that time shadow signal will call the original function that the resource is empty, you can come, so that the time will not be wasted in waiting for the original resource, and shadow will handle that waiting queue thing. Okay, so that's what is the how do we overcome the busy waiting in the semaphore. And once a semaphore is ready, wake up signal is called. Okay, it is sent to all the process that enters the semaphore. Okay, next is the deadlock and starvation within semaphore. What is a deadlock? Okay, deadlock means that suppose you have imagined a highway in which one car is coming like this, and that car is blocked by this car, and this car is blocked by this car, and this car is blocked by this car. In this case, none of the cars will move. Okay, that is called as deadlock. Each car is waiting for the other car to move. Okay, like you can also imagine a highway in which one car is coming like this, car is coming like this, and it's a one way. So this is waiting for this to move, this is waiting for this to move. So in this case, this there is no movement happening. Okay, because of waiting for each other. That is called as a deadlock. And starvation means none of the car is getting the chance to move, and both of them's task is not getting executed. That is called as starvation. So let's understand the deadlock within semaphore using an example. There is a process P naught, there is a process P1, and P naught is waiting for S first. It has called wait S, and P1 has called wait Q. So the P naught is waiting for S, and P1 is waiting for Q. Next, after this, it will go and call wait Q. Since P1 is waiting for Q, this will not be given to P naught, right? P1 is already waiting for Q, so P1 will not be given Q. Okay, and when will P1 release this? See, if P naught wants this, P1 should release this, right? When will this be released? This will be released when P1 gets S. But who is controlling S? S is controlled by P naught. So what's happening? P naught wants Q, but P1 is utilizing Q, and P1 wants S, but P naught is utilizing S. So either of them should do it first, but they will not do it first because it is designed as they should wait for each other. This situation is called as deadlock. Okay, and starvation happens when the indefinite waiting comes and the one process does not get a chance to execute. When does this happen? When LIFO is used. What is LIFO? Last in first out. Okay, so suppose that there is a stack of books here and one book is present at the end, and new books are coming and taking out, another book is coming and it's getting taken out, and like that many books are coming and going, but the last book which is there, it will always be present at the last only, because once all the above books will be over, then only this book will be accessed. But in LIFO that will not be happening, right? In case any other new book comes and it will be executed, and another new book comes, it will be executed like that. Okay, so in that case, the last one which is present, that will not be executed for indefinite amount of time. That is called as starvation. Okay, let's discuss the classical problems in synchronization. So there are three types of problems, classical problems in synchronization. First is bounded buffer problem. Okay, you remember we discussed the producer consumer problem, where producer is producing the stuff and consumer is consuming the stuff. But if producer's speed is more than consumer, there will be a problem. If it is less than consumer, then also it will be a problem. To overcome this problem, we will be using a buffer. Buffer means another empty space. If producer is producing more, it will be stored in empty space, and whenever consumer can consume, it will be consuming from the buffer. That is called as bounded buffer problem. Okay, we use buffer to store extra packets. N buffers can be used where each buffer can store one value. Okay, next is the reader writer problem. Reader writer problem, here what happens is, suppose that there is a document here. Okay, in notice board of your college there was one document and some news is written here. Okay, and all the students are watching that and reading it. Okay, so what happens, one person comes and edits it. Okay, one person comes and make changes to it. So they will be reading some other information than what other people before them had read, right? So once this is modified, they will be getting some other information than what other people had known. And if another writer comes and modifies it again, the next batch will read it something else here. So what happens here, if writer is given the capability to write and change, if multiple writers can write and change at the same time, every other reader will get a different information from the notice board, right? So to avoid that, only read data should be given, so that no writer can write. Even if a writer can write, only one writer should be given. If multiple writers are given, then obviously the information will be overwritten and changed. That is called as the reader writer problem. At a time, only one writer is allowed to edit the data. Okay, next is the dining philosopher problem. Okay, in dining philosopher problem, imagine five philosophers are there: P1, P2, P3, P4 and P5, and they are sitting in a dining table which is of circular, and here the plates are there. Okay, these are the plates of the philosophers, and philosophers has two tasks: either they eat or they think. Okay, either they eat or they think. Okay, either they eat or think. Whenever they are eating, they'll not be thinking. If whenever they are thinking, they'll not be eating. Okay, like that. And these are the chopsticks present here. Okay, so totally five chopsticks are present here, and five philosophers are sitting here. Five plates are there, and in between you can see this is food. Okay, a bowl of rice is present. Now, whenever a philosopher is hungry, so suppose that P1 is hungry. Whenever P1 is hungry, they want to eat the rice. Okay, so to eat the rice, they have to grab two chopsticks from the neighbor's end, and they have to use two chopsticks to eat a bowl of rice. So in case this philosopher has taken these two chopsticks, P5 and P2 cannot eat. Why? Because they need two chopsticks to eat, but this chopstick is already being used by P1. In that case, P2 and P5 cannot eat. Only who can eat? Either P4 can eat by using these two, or P3 can eat by using these two. Okay. So suppose what happens is, each philosopher coming to his ego, what they do is they will take one chopstick and keep it with themselves. Okay, one chopstick he will keep, one chopstick he will keep, one chopstick he will keep, one chopstick he will keep. So in this case, everyone has one chopstick and chopsticks are over, and no one is eating because they cannot eat with one chopstick. This case, what happens? A deadlock happens. Each philosopher is waiting for the other philosopher to release one chopstick so that they can start eating, but that philosopher is also waiting for the other philosopher, and so on till it reaches the first philosopher. So this is a analogy given in the situation where this is the resources and these are the processes accessing a resource that will be coming in a deadlock when one process is waiting for the other process to release the resource, which is waiting for another process to release some resource, and so on. So to avoid this problem, we have some solutions. Okay, you understood what is the problem. Now solution is that represent each chopstick as a semaphore. So each chopstick should be represented as semaphore, so that once a lock is present, other philosophers cannot take that chopstick. Grabbing a chopstick is denoted by wait. If one chopstick is taken, it should be calling the function wait, requesting for the resource, and once it is released, the chopstick is kept back to the table. It should be mean signal should be called to inform the other philosophers that chopstick is released. You can use it. Allow at most four philosophers to be at the table at the same time. Philosophers should pick the chopstick only if both chopsticks are available. If one chopstick is available, don't pick it, otherwise it will lead to deadlock. Odd number of philosophers pick first left, then right, and even number of philosophers pick right, then left, so that same chopstick will not be picked by two people. Okay, like that. That is about the philosopher's dining problem and its solution. Moving on, we have the monitors. Okay, what do you mean by monitor? It ensures only one process is active within the monitor at a time. Monitor is one space here where the processes are present here, and one of them should be active at one point of time. And to have a powerful synchronization, a condition is deployed. What is a condition? Condition can be either wait or signal. Wait condition can be there or signal condition can be there. Wait means a process that invokes the operation is suspended. Whenever wait is called, the process will be suspended, and whenever signal is called, the process suspension will be resumed from the wait state. Okay. And a solution to Dynast philosopher problem could be implemented based on the operations pick up and put down. When this is same as this one, pick up means the chopstick is picked, and put down means the chopstick is put down. Okay. When utilizing a resource, wait must be called and resuming a signal must be called. Okay, these two things. And another semaphore next is used to keep track of the next process which needs to be executed. Here another semaphore is also used. Now suppose that multiple processes have requested for a resource. Okay, and all of them are waiting. Now when the resource is released, which of them will be given the chance to execute the resource? So the one which is requested first, they will be given the first priority. First come first serve will be used in case multiple processes are requested. Means whichever process requested first, they will be given the chance to execute the resource. Okay. Moving on to the second half of the module, which is regarding the deadlocks. So this is a visual representation of deadlock. Imagine four cars are there: C1, C2, C3, C4. C1 wants to move in the right direction, but it is blocked by C2, which wants to move in the down direction, which is blocked by C3, which wants to move in the left direction, which is blocked by C4, which wants to move in the up direction, and C4 is blocked by C1, which wants to move in the right direction. In this case, none of the car will move, and this is the situation of deadlock. Okay, and in that we have some concepts to understand the deadlock in the terms of process and resources. So what is the system model? A system consists of a finite number of resources to be distributed among a number of competing processes. Okay, resources will be there, finite number of resources will be there, and there will be some processes P1, P2, P3, and all of them will be requesting for some resources, and which process will get what resource, that things are present in the system model. So a process must request for a resource before using and release it after using. Okay, it should not hold it. Now, deadlock characterization. So deadlock occurs when one of the four conditions which are given here will be not one of the four. When all the four are there. Okay, necessary condition. So there are four conditions. If all of these four are there, means none of them should be not there. Okay, all four should be there. Then only deadlock will happen. Okay. So what are those necessary conditions? First is mutual exclusion. Only one process should be able to execute a resource at a time. If another process requests for the resource, it must wait. Okay. If this is there and hold and wait is there, if a process is requesting a resource, it is also holding a resource. Okay. It is holding one resource and it is then also requesting a resource. Okay. That is the second condition. Third is there should be no preemption. If there is no preemption, means the resource which is held by a process, none of the factors can preempt it, means stop it from holding it. Okay, in that case the process will continue holding it as much as it wants. Next is circular wait. Circular wait, as I discussed, is a deadlock. P naught is waiting for P1, P1 is waiting for P2, and so on till Pn, which is waiting for P naught. Okay, that is circular wait. If circular wait also exists, preemption is not possible, and each process is requesting a resource by holding another resource, and one process can be executed. One process can execute a resource at one point of time. If all these four conditions are met, then deadlock will occur. Okay. Now, this thing can be represented visually using a resource allocation graph. Okay, so the squares and the rectangles you see are the resources, and the circles you can see is the processes. Okay, and from Ri, which is resource I, to process I, if there is an arrow, means resource I is allocated to Pi, and Pi arrow is there to Ri, means Pi is requesting for a resource I. Okay, so as you can see, R2 is given to P1 and P2, and P1 is requesting for R1, R1 is given to P2, and P2 is requesting R3, R3 is given to P3, and R4 is present, and none of the processors requested that. So this is the way you represent which process is requesting what resources. Now, if a graph contains a cycle, there is a deadlock which might occur. Okay, cycle means this is requested. R2 is given to P1, P1 is requesting R1, R1 is controlled by P2, and P2 is requesting R2. In that case, if the arrow was like this, last arrow, if it was like this would have been a deadlock situation. Okay, because P1 wants R1 and P2 wants R2, but R2 is controlled by P1, and R1 is controlled by P2. In that case, each process what they want is controlled by other process, and they are waiting for the other process to release it first. Okay, in that case deadlock will occur. Now, what are the methods for handling deadlocks? Deadlock can be handled in one of the three ways. Prevent the deadlock, okay, by using some algorithm, and in case deadlock has happened, detect it and recover from it, and assume that deadlock never exists. Means build a situation such that deadlock will never happen there. Okay. Okay, so here two things can be there. Okay, to ensure deadlock never occurs, a system can either use deadlock prevention, where ensuring any one of the condition necessary for deadlock does not hold. Means I told you four conditions are there for deadlock to occur. If any of these four condition is not there, okay, any of these four, like hold and wait is not there, but these three are there, deadlock will not happen. Like that, any of the four are not present, at least any of the four, in that case deadlock will not happen. So deadlock prevention algorithms are there which ensure any of the deadlock condition will not occur. Okay, and second is deadlock avoidance, by taking steps to ensure that deadlock state does not take place. Okay, we are ensuring it before only that deadlock state only should not take place, so that deadlock will be avoided. Now let's discuss what are the algorithms present in deadlock prevention. So deadlock can be prevented by ensuring at least one of the four conditions are not met. So if you want to ensure mutual exclusion is not met, in that case you have to give all the processes the chance to use the resource R, right? But that will not be always possible. This can only be possible when there is a read only, because all the process can read only one resource without changing it. So there is no problem in that. But apart from this, mutual exclusion is not possible, because it will cause inconsistency in data if multiple processes start to edit the data, same data. Next is hold and wait. Ensure that when a process requests, if a process P1 wants to request, Make sure the P1 should not have any holded data. If it has holded data, it should not allow to request. If it does not have a hold data, then only it should be allowed to request for another resource. Okay, that can be used for making the condition not met. And no preemption, that should not be there. Allow preemption for the resources. If one process is holding for one resource for a long amount of time, preempt it, break the connection, and use and give it to the process which requires it to execute. In this case, no preemption will not be valid, and circular wait will not be valid when we ensure that total ordering of all the resources types are present. So the required resources execution should happen in increasing order of enumeration. All the processes will be having the numbers, and based on the numbering only, they will be given the chance to execute. So the circular wait will not happen because the order is already defined. There is no waiting concept here. Next one is the deadlock avoidance. How do you avoid a deadlock from happening? Okay, so to avoid a deadlock, what we need to do is we need to have a system setup in which the deadlock will not happen. Okay, so let's have a look at what are the concepts present. So avoidance method requires each process declares maximum number of resources of each type. If all the process declare that I want so and so many resources, in that case the deadlock can be avoided because process will not be taking up more than what they have requested for. Okay, so getting to know maximum number of resources of each type which the process requires, this information can help avoid deadlock. Okay, what is safe state? It is defined as a state where the system is able to allocate all the resources to each process, avoiding a deadlock. Safe sequences, in which sequence if the process requests for the resource there will be no deadlock. Okay, now to implement the deadlock avoidance we have an algorithm very important from exam point of view, which is Banker's algorithm. Let's understand this using an example. Okay, what does Banker's algorithm do? Okay, so see here you have a few columns here. This is the process column. Okay, which processes are there? Let's assume P1 till P5, five processes are there. Allocation means how many things are allocated here. Okay, how many resources are allocated. Okay, so allocated means how many resources are allocated initially. Okay, let's suppose that there are three types of resource, A, B, and C. Okay, and A has 10. There are 10 A resources, and there are 5 B resources, and there are 7 C resources. Okay, 10, 5, and 7. Okay, so now out of 10, 5, and 7, for P1, already A has allocated 0 resources, and P1 has 1 B, and P1 has 0 C allocated. Okay, so like that only P2 has 2 A's allocated, 0 B's, and 0 C. P3 has 302, and so on. So let's calculate how many resources are already allocated. To calculate that, just add up 2 plus 3, 5, 5 plus 2, 7. 7 A's are already allocated, 1, 2. 2 B's are already allocated, and 2, 3, 4, 5. 5 C's are allocated here. Okay, so as you can see that there are some resources allocated, 7, 2, and 5. 7 A's, 2 B's, and 5 C's are already allocated. Now P1, if it wants to execute totally, it wants 7 A's, 5 B's, and 3 C's. P2 wants 3 A's, 2 B's, and 2 C's. That is the maximum need of each of these resources to get executed. Okay, now available means how much it is available at one point of time, that we will fill as we go. And remaining need, see, maximum need is 753, but allocated already it is 010. So the remaining need is 7 minus 0, and 5 minus 1, and 3 minus 0, that is 743. The remaining need for this one, the P2, is 322 minus 200, that is 122. So this is the remaining need which is requires after the having the allocated ones, so that it executes successfully. Okay, like that all for all it is given. Now to solve the Banker's algorithm, all you have to do is count the available ones. Okay, now see, 7, 2, and 5 is already allocated. With that resources we don't have from 10, 5, and 7. So subtract 10 from 7, and 5 from 2 from 5, and 5 from 7. So it will be 3, 2, 2. Okay, so how many resources we have available? 3, 2, and 2. Now very simple, what you have to do is you have to check 3, 2, 2 is available. Which of these processes can I execute with the remaining with the available resources which I have? Can I execute this one? No, because 3 is here and 7 is here. I cannot execute. All of them should be satisfied. Even A's number should be satisfied, B should be satisfied, and C should be satisfied. Then only I can take it. What about the P2? 1 2 2 is the requirement, and I have 3 2 2. So if I give 3 A's, if I give 1 A from here, 2 B from here, and 2 C from here, it will execute. Right. So this is one of them. Right. Based on the available resources, I can allocate it to P2. Okay, let's see the other ones also. 600 I cannot allocate. It is 3 here and it is 6. It will not be satisfied. 211, can this be satisfied? Yes. 3, from 3 I can give 2. From 2 I can give 1. From 2 I can give 1. So this can also be satisfied. 531, no, it cannot be satisfied because it is 3 and its requirement is 5 here. So either this one or this one we will take. We will go in sequential order. We will take this one. So once I give 1 from here and 2 from here and 2 from here, this process will utilize that resources and execute and completely successful. So once P2 is successful, at that time it will also release the resources which it had allocated initially. It will release 2 0 and 0, because once this is over it does not require these resources anymore, so it will release it. If it releases, it will get added up in the available ones. See, this resource is released means this can be used, means whatever can be used, that means that is available, right? So total available A's will be 2 added with 3, 0 added with 2, 0 added with 2. So total available will be 5 2 and 2, and P2 is executed. Let's write the sequence. P2 first can be executed with the available resources. Now, after P2, can this be executed? 600, 522? No. 211 can be executed with 522? Yes. And once P4 executes, it will release the resources which P4 had holded. P4 had holded which resources? 211, add it with 522. When you do that, you will get here 733. Next, 531 can be satisfied with this. Yes, it can be satisfied. So P5 will be executed and the resources held by P5 will be released. So what were the resources held by P5? 002. So 002 will make it as 735. Now after this is over, go back here and check here 743. Can this be satisfied with 735? No, it cannot be satisfied. Why? Because 4 requirement, here it is 3 only. Okay, so this cannot be satisfied. We'll move on. P2 is over. It will come here 600. Can 735 satisfy 600? Yes, it can satisfy. So P3 will be executed. After P5, P3 will be coming here and it will release the resources which it had hold, that is 302. So when it releases, it will become 10 and it will become 3 and this will become 5 plus 2, 5 6 7. Okay, now all the resources are executed and only one is remaining, which is this. Okay, but can this be executed? 7 4 and 3 is requirement true. 10 3 7. See, again requirement is coming less, but that should not happen. That means I have made some mistake in my calculation somewhere. See, the mistake is happened here. Okay, see, I had 5 here, the available resources, and here the allocated ones were 7 to 5. So 5 minus 2 is 3, but I took it as 2 here. I should have taken it as 3. So one I had missed. One I had missed means here I should add one, right? Here it is 4. Okay, and here also it is 4. Okay, and here also it is 4. Got my point? So once, and in this position also this could be have executed, that also you can take. So here instead of P3 it could have been P1, because from P5 we went to P1, right, and checked it was not possible, but it will be possible. Why? Because 745 is present and 743, this will be executed first. P1 will be executed, and when P1 will be executed, 010 will be released. When 010 will be released, at that time the number of resources available will be, it will be 7 5 5. Okay, from here 7 4 5 7, it will be 7 5 5. Okay, and after P1 only P3 will be remaining, and P3 will also be executed. 755 will satisfy 600. So 302 will be released. Okay, so it will get added up here. In 302 it will be 10 and it will be 5 here, and 5 plus 2 it will become 7. Last it will execute P3. Okay. So this is a sequence. If in this sequence, if they go using this available resource and allocation in this particular scenario, if P2 requests first, then P4, then P5, then P1, then P3, then deadlock will not happen. This sequence is called as safe sequence. Okay. Moving on, we have deadlock detection. Okay, how do we detect if a deadlock is present? Okay, as I told you, we'll be using a resource allocation graph for visually representing if the resources and the processes which are present. We'll be visually representing it using resource allocation graph, and we'll be also having a wait for graph. Okay, let's understand what is wait for graph. Now, this is the resource allocation graph given here. The resources are given by the squares and processes are given by the circles. This indicates that R4 is utilized by P1 and P1 has requested R1, but R1 is held by P2 and P1 has requested R3, R2. P1 is utilizing P1 has requested R3, R2 and R5, and P3 is utilizing R2 and it has requested R5, and P4 is utilizing R5 and P4 is requesting R4. Okay, like that this graph is present. Now, using this graph, how do we calculate this graph? Okay, let's consider one process at a time. See, P1 is here. Okay, now P1 is requesting R1, but R1 is utilized by P2, so P1 is indirectly requesting from R2. P1 is indirectly requesting from P2, so P1 is indirectly requesting from P2. Make a point here. Okay, like that for P1, and P1 has R4. R4 who is requesting? P4. So P4 is indirectly requesting from P1. So P4 to P1, like that. Okay, P5 is here. So P5, and P2 is requesting a resource held by P3. So P2 is requesting from P3. So P2 to P3, P3 to P4, and so on. Okay, like that we'll make the wait for graph. And if in this graph anywhere you find a cycle, okay, if you find a cycle, that means there is a deadlock. Okay, if there is a cycle, that means there is a deadlock. See, you can think that there is a cycle here. Okay, this can be a cycle, but it's not. Why? Because P2 can also go here and here, right? The cycle means there should be no other choice, like this from here, this from here, and this from here. That's all. There should be no this. This is called a cycle. If there is a cycle, means there is a deadlock. Okay, that is how you detect the deadlock. And after detecting, how do you recover from the deadlock? Recovery can be done in two ways. There are two ways to recover from deadlock. First is process termination. Abort all the deadlock process which are present, or abort one process at a time until deadlock is removed. That is one way. Second is resource preemption. Select a victim, rollback, and starvation. See, resource preemption means when one process is holding and using one resource for a long time, preempt it in between, and means selection of victim means preempt this resource, and rollback means take it back to the position where it was there without having to use that resource, that is rollback. And once you roll back, ensure that starvation does not happen, so that this process after some time get another chance to use this resource. Okay, that is to avoid the starvation. Okay, like that we can recover from the deadlock if it's present. Okay, so that's all for this video, and if you found this video helpful, please like and subscribe. That helps me make more videos like this. Thank you so much for watching. I'll see you in the next one.